Hello everyone. In this session, we will discuss statements involving multiple quantifiers. Having learned statement with the quantifiers and its negation in the previous classes on the course of Foundation in Mathematics, we would extend this topic for a multiple quantifiers. So let's begin with some examples and let's see how this the quantifiers get involved in a statement. Okay, so let's take this example S1. In this S1, the statement says in every shelf in the library there is a mathematics book. Okay, now you observe that at first step there's a universal quantifier that is used in every shelf in the library. So you are talking about set of shelves in the library. So definitely your set of context is going to be set of shelves in the library, and you're talking for every element in the set of context. So universal quantifiers, and the property in this case that in that shelf there is a mathematics book. So there is a mathematics book itself in the shelf is a property. So again you will say that the property itself contains quantifier. So first we will break this into this. We can read the same statement as using quantifiers. For every s in x, I denote the element. So x is a set of shelves in the library. I denote it as red s. So every s in x, the property is that there is a mathematics book in s. Okay, given any shelf in the library, there is a mathematics book in S. Now, if you look at the property, it contains a quantifier. There is existential quantifiers. But what is the set of context in this case? Okay, the set of context will be the set of book in the shelf which you have chosen, that is S. Okay, so what you will say, you will be very precise while defining the set of context. It is not just the set of books, but set of books in the shelf S, in this S, and that's why I have denoted it in red. So here again, to break down this into two parts, we denote BS. Why BS? Because the set depends on which S you are choosing from X. So it depends on the element. So whenever the set of context depend on an element, we denote it by that. So BS, set of books in the shelf S. So for example, if I choose say T is the one shelf in the library, for that the set of context will be BT, and like that it goes on. Okay, so B is the set of books in the shelf S. So again we can break the given statement in this way. So the first part will remain as it is for every S comma X, the whole thing in bracket as it is. Now this can be written as there exists B in BS such that B is a mathematics book. So that B is a being mathematics book is the property of this statement involving existential quantifiers. Is that clear? Now to negate the statement, it would be very easy if you refer to the last one wherein you have written in a mathematical format, because you know that negation of universal is existential by and you have to negate the property. Same way negation of existential is universal by negating the property. So how do we negate this statement? How do we negate this S1? Just look at this S1, because reading the S1 in a English phrase and negating it as it is might be a very complicated task. Okay, so if I look at this note of S1, first negating the universal quantifier. So there exists S in X. A set of context X and BS will remain as it is, such that you negate this part now. Such that you will be negating what is in this first bracket. So how do you negate this kind of statement involving existential quantifier? You will say that for every B in BS, this is not true. B is a mathematic book is not true. So that is same as saying B is not a mathematic book. So you will say that for every B in BS, B is not a mathematics book. Got it? So that would be, very simple task to just refer the statement in a mathematical format and negate it. Okay, now let us see what does it means. So if I write down in a simple language, there is a shelf. What does this stand for? There is a shelf as in the library. There is a shelf in the library in which each book is in which each of the books is a non-mathematics book. That means there is a shelf in the library which does not contain any mathematics book. So that is as simple as that. So you can now compare this statement with this statement. You will see that it is exactly negating the statement. So what happens sometime, you don't have only two quantifiers in this. Like in this case, you have only two quantifiers. You may have more than that involved in a given statement. So if you look at the compact or the mathematical form of writing it using negation, using quantifiers, and using the fact that the negation of universal is existential and the universal of existential is a universal statement, only negating the property, you can very easily negate the whole statement. Okay, so that's what. Let us take one more example. In this case, what happened, we have taken universal quantifier first and then existential quantifiers. Let's see one example. S2. There is a shelf in the library in which all books are storybooks. So first let us split this. So when I read this at the first time, we see that there is a shelf is the existential quantifier, and you are talking about the shelf in the library. So set of context will be set of shelves in the library. So there is at least one shelf in which all books are storybooks. So the property in the first step will be in that shelf all books are storybooks. So we write it in this way. There exists S in X such that all books in S are storybooks. Now again, if you look at the property, it itself contain universal quantifier. Okay, now what you are saying that all the books in S are storybooks. So you are referring to the books in S. So the set of context will be the books in the shelf S. Okay, and we will again use the notation which is dependent on this S. Okay, now here this S may this S is what S you have chosen over here. There exists, you are saying. So for all book in S are storybook. So the property will be that the book is storybook. So how do we write down this? We write it in this way. The set of context BS for this later part will be a set of book in the shelf S. So I can write down S2 in this way. There exists S in X such that for every B, again I use the notation that is your choice, a dummy variable. So for every element in BS, B is a element is a storybook. So for every B in BS, B is a storybook. Again, negating the statement, it won't be a difficult task if you just look at the statement and just look at the statement with the quantifiers, and it is which is written in the mathematical form. So what you will say that for every S in X, you give me any shelf in the library, I'll be able to find a book in that shelf which is not mathematics, which is not a storybook. Negation of this, right? So given any shelf in the library, it has a non-storybook. That's what it means in a simple English language. So these two examples shows you how you can negate the statement involving multiple quantifiers. Now here in this both of these examples, the alternate quantifiers that we have used are like there exist and for all and there exist. You may have both the quantifiers at the same time also. So let us take some more examples. Now here in this examples which we are discussing may be taken from the part real analysis. So those who are not familiar, those who have not learned the course real analysis, they may skip this example. Like for example, the first one as A is bounded above in R. Okay, A is bounded above in R. When I say A is bounded above in R, what do you mean by saying that the set A has an upper bound in R? So first of all, you should say that there exists upper bound for A. So there exists alpha in R, so that is an upper bound, such that alpha is an upper bound, of n. What do you mean by saying alpha is an upper bound? For every element in A, that element has to be less than or equal to alpha. So that's what you mean by saying that the set A is bounded above. If the example was simply given as the statement was given as set A is bounded above by alpha, in that case you would have only a statement involving this quantifier. Now you are saying that it is bounded above, so that means you are defining the term set being bounded above. So you have to say that there exists it means what? There exists upper bound, there exists an element in R which acts as an upper bound for the set A. So now it's very easy to negate. So when do we say that the statement say that A is not bounded above? When would you say? You give me any real number, it will never act as an upper bound for A. So exactly what does it mean? For every alpha in R, there exists x in A. There is at least one x in A which will not satisfy this property, x is less than or equal to A. So its complement is only that x is greater than A, and so that's what it says, that A is not bounded above. So in a simple word, A is not bounded above in R. Okay, so that's a first example. Second example, everyone knows the definition of onto, onto being the function being onto. So f from x to y is onto. When does it happens? When this y is entirely equal to range of f. That means every element in y has a pre-image. So how do you say that? So for every element in y, there exists an element in x such that f of x is equal to y, right? That's what exactly we have. For every y in y, there exists an element in x such that f of x, that element is equal to y. How do you negate it? That means it's same as saying that there is at least one element in y which does not have a pre-image. So basically, when you use when I say it in that way, it's becoming complicated to write it down. So how would you write it down? There exists y in y such that for any x in x, f of x will never be equal to y. Okay, that is same as saying f from x to y is not onto. Okay, this is a very common, even those who are beginning with the mathematics course, you can think over this example. The second one, the first one is you might not be familiar with that, as it's a example in the real analysis, the term in real analysis. Now here are some mathematical as well as non-mathematical statements for you all, which includes more than one quantifier. So I expect you all to solve this problem, solve this exercise. I would stress on this fourth example, wherein both the quantifiers which are used are universal. You can see that every tree in the campus has all of its leaves green, right? You can write down this again with the standard notation of mathematics. Both the places you will have for every, no problem. You proceed with that. It might not you might not be comfortable in reading that statement, but when you put it in the quantifier form, it is understood that it can be read in this way. Okay, now this is a very important note. It basically tells you the meaning of the statement. For every x in x, there is a y in y such that y has property p. When you have this kind of statement, the existence of y depends on x, may depends on x. Sometimes it may not, but it depends on x. Okay, so the element y may depend on x. The choosing, when you are saying there exists, that means you should be able to find that y. So when you will be able to find y, when that depends on the element x in x. Let's take one example to show the what exactly I mean to say. See, for every human being x, there is a human being y such that is a father of x, such that y is a father of x, right? So now this is a true statement. Everyone knows that for every human being there. Okay, now I have a human being x, so this y obviously will depend on x, because I cannot call any human being as a father of x, right? So depending on what x you are choosing, or on what x you have over here, you will be choose your y. Okay, let me take one example which is more closer to mathematics. For every x in r uh, star, this is a set of real number except with the element 0 in it. For every x in r, there is an element y in r. For every x in r star, there is an element y in r such that xy is equal to 1. This is basically the property which is called as existence of multiplicative inverse. What is happening for every x in, for say suppose I take 2. For 2 in R, there is a y such that xy is equal to 1. So what y you can choose? 1 by 2. So that 2 into 1 by 2 is equal to 1. See, if I have x equal to 3, then y in that case will vary, 1 by 3. So that's what it says. In this case, y depends on the value of x you have. Okay. So that's why whenever you have this statement, for every x in x, there exists y in y such that y has some property p. The existence of y depend on the value x. Again, next note says that the order in which the quantifier appears in the statement is important. If we change the order, the meaning of the statement may change, and if it changes, then it will create a havoc. As you can see in the first statement, if I interchange the quantifiers, you can see that you have first universal quantifier and next you have existential quantifier. Now if I write down existential quantifier first, if I say that there is a human being y such that for every human being x, y is the father of x, does it make sense at all? So it's same as saying there is a common father for every human being, which is not true. Okay, which does not make sense. And but definitely the first statement, this on the first note, does not convey the same meaning as the first statement in the second note. Okay, so which means that there is a human being who is a father of every human being, which is okay. So the first statement is true, whereas in the second note the first statement is false. Same way, if I interchange the quantifiers in this, if I say that there exist if I say that there exists y in R such that for every x in R star, xy is equal to 1. Again, so you are saying that the multiplicative inverse is common for any x. That's not true. That's not true. Okay. There is a real number which is a multiplicative inverse of every non-zero number, which is not true in mathematics, right? Okay, let me take some more example closer to mathematics. A is bounded above in R. Is as same as saying there exists alpha in R, such that for every x in A, x is less than or equal to alpha. Now, if I interchange the quantifiers, what I will have is this: for every x in A, there exists alpha in R such that x is less than or equal to alpha. So that means your upper bound alpha is not unique in this case. It will keep on changing for different value of x. So that that says that this does not, both the statement does not convey the same meaning. Okay, so are these two statements the same? Definitely not. The second statement was true. If the second statement was true, then every subset of R would be bounded above. Yes, because why? Because for every x in a subset of R, I'll be able to find any real number which is greater than or equal to that given element in A, right? So therefore the order in which the quantifier is appearing in the statement is very important. So you can make a similar observation for this following example. The first one is existence of additive identity, and the second one is existence of additive inverse. Okay, so that's all for this session. In the next class we will talk about the compound statement and its negation. Okay, thank you.